Hello. Hello. Oh, let's try that again. Hello. Oh, a little bit. Hello. Let's see if I can say the first word. Get through the rest of it. It's gonna be real good. Hello and welcome, all you intellectually curious, beautiful people, to Math Monday, number 5. If you watched last week, number 4, I talked about the practical math that everybody seems to want to know so much about, and then it's like, oh, that's really boring. Yeah, practical math is really boring. In math, so much of the time we have this problem where the useful stuff people don't actually like because it's boring, and then the not useful stuff, people are like, well, what's the point of learning this because it's so difficult and I can't use it anywhere. How did that become the only measure of knowledge's worth, was how useful it was? I don't really get that, because so much of the math that was discovered by these brilliant mathematicians and scientists was not for the sake of usefulness, and then guess what? Became very useful. And I think sometimes we forget to be intellectually curious and to really foster that in ourselves. Today I'm going to start with the basis of all that confusing and not confusing math and boring math and good math and all the stuff, and that is the number system. All right, when we're talking about number sets, we're talking about sets of different types of numbers. A set is a set of distinct elements. So our elements here are 1, 2, 3, 4, things like that. So 1 is different from 2, is different from 3, is different from 4. That's what a set is. So first we have our set of natural numbers. That's just your counting numbers, 1, 2, 3, 4. We use this n with a little dash through it to denote natural numbers. Now, a really interesting philosophical question is, were natural numbers created by humankind, or did they just exist inherently in our universe already? Really interesting question to think about, but I'm not going to go too far down that rabbit hole right now. The next stage up is our whole numbers. There's no special thing to denote whole numbers because usually it's just put into the integers when you get into higher math. It's the natural numbers plus 0. That's all it is. People are like, why do you need a whole other number set for that? Because 0 is really important. It wasn't even a number forever. The Babylonians, they just used the 0 thing as a placeholder for nothing. And then the Indians came along and were like, yeah, no, 0 is actually really important. One thing I want you to know about 0, there's a difference between nothing, which is what 0 is, and something never having existing, which is not what 0 is. So when you spend all your money, you have $0 left. Means you had some money, but now it's all gone. Doesn't mean you never had any money in the first place. So next step up is integers. When we start thinking about 0, we start thinking about, oh, there can be numbers less than 0. We use a z for integers because I is used for something else. So what's not used a lot? Z, so let's just use that. So these are -3, -2, -1, but that we can go super duper negative there. And then we also still have our whole numbers and natural numbers included in this, which is why I've drawn the circle around both of those things, because integers still include the whole numbers and natural numbers. And then integers are included in our rational numbers. So rational numbers include all our integers, our whole numbers, our natural numbers, because what rational numbers are, which is what we use the Q to denote, is any number that can be expressed as a fraction. Okay, so if you have a decimal that ends, so terminates, or repeats itself, this is a rational number, okay? For example, 0.2, that's the fraction of 1/5, so it can be expressed as a fraction. 1/3, that's a fraction that has a really interesting decimal that never ends. It's 0.333333333 that goes on forever, but that 3 continues and it repeats itself, right? So that's a rational number. You can take any integer, whole number, and natural number and express it as a fraction by just putting it over 1. So for example, -9, we express that as -9/1, because when you put something over 1 means you divide it by 1, which means nothing happens. All right, so take two numbers, two natural numbers or integers, put one in the numerator, top spot, put one in the denominator, bottom spot, and you have a rational number. So for example, 11/17. Okay, those are all our rational numbers. That's kind of where I'm going to stop building on each lower set and make a whole new set of numbers, and that's our irrational numbers. So these are numbers that are not easily worked with or found in our natural universe. Irrational numbers are completely disjoint from rational numbers. And what they are is they are non-terminating, non-repeating decimal. So that means no number in existence can be both rational and irrational, because that would be irrational. All right, so a very classic example of irrational numbers are square root of 2. There's no two numbers that are exactly the same that multiply together to get 2, or at least the two numbers, or the number that does, that multiplies itself to get 2 is an irrational number. Another example would be the cubed root of 4. What number multiplies by itself 3 times to get 4? That's an irrational number. There's some naturally occurring ones in our universe. Mathematicians get so excited when we find a new naturally occurring irrational number. It's a little bit nerdy. But the most classic example is pi. If you take the diameter of a circle, multiply by pi, you have the distance around the circle. E is a special irrational number that actually a lot of our exponential growth in nature is based on. There's tau, which is just 2 times pi, which some people like a lot better than pi, which I will definitely be doing a future Math Monday video on. You guys can count on it. That's our irrational numbers there. We encapsulate all those rational numbers and irrational numbers together. We call those the real numbers, okay? Because they still are tangible numbers that we can use in everyday life, okay? Those are real numbers. We use this special R thingy for it with the little dash through it. And real numbers are pretty awesome. They're pretty great. And usually you never have a need to go past that. That does exist though. We do have something called imaginary numbers. It's all based around the square root of -1, which can't be possible because you can't have two numbers multiply together to get a negative. So that's completely separate from the rational numbers. But if I add the real numbers. But if I add some real numbers and imaginary numbers together, I get something called complex numbers. And that just starts getting way out there. Anyways, that's it for today. I really want to do this video just because obviously you can see that there's a really rich base of information here that I can go into in more depth, but it'll be really nice to be able to go back and see how it fits into the bigger picture. So thanks for sticking with me through the whole thing. I hope you guys have an awesome week. Happy Monday.